Okay, we're going to continue our discussion here with binary eutectic phase diagrams. We didn't get finished earlier, so let's put up some points here that we know, of course. And on this one, of course, this is all going to be liquid, and it will be obviously circle P equals 1. This is a solid solution of A and B, but it's B rich, and I'll put that down here. Anyway, so this is going to be a circle P equals 1, and this is of course, solid solution of A and B, but it's A rich, so this is also just single phase here. So obviously between a single phase and a single phase, we have a two-phase region, of course, and then the same thing here, circle P equals 2, and then of course between this single phase and this single phase, the alpha and the beta, this is going to be a two-phase region. Now let's look at some interesting things. First of all, excuse me, we know that this line represents the liquidus line. This line represents the solidus line because again it's going from solid to a liquid here. All right. But what about this line right here and right here? Because now this is a single phase solid going to a two-phase solid, so we give this a new name, and we're just going to call it the solvus, S-O-L-V-U-S, the solvus line. Again, going between a single phase solid solution to a two-phase solid solution. So that's what the solvus is all about. Okay, now let's look at, let's define what alpha is here. Alpha is basically a solid solution of A and B, a solid solution of A and B, but it is A rich. It's much more A in it than over here than there is B, element B. And beta is also a solid solution, of A and B, but it is B rich over here on this far side over here where beta exists. All right. And then of course L is just a liquid solution of A and B. Okay. Now again, this point, this eutectic point, which also obviously equals the eutectic temperature, but it is like a triple point because now we have equilibrium, and here we have at this point we have alpha equals beta equals liquid, all right here. Okay, so what's taking place here is that at this one point, this one temperature and this one composition, we have the eutectic point, which again is evidenced here by the lowest melting temperature on the whole diagram, because we have freezing point depressions going in both directions here. But it is an equilibrium point because now we have all three of these existing. So notice that from this liquid, it's going to decompose down here into a solid solution of alpha and beta directly from pure liquid. So what we're going to experience here is some new types of products here as we go through this analysis of this, and I'm going to share that with you here in just a minute. But so this is a very important point here, this eutectic point, and all right, and it's something that we interested in knowing something about, because if this was two components like solder, okay, like lead and tin, you would want to try to find the lowest temperature that solder would still remain liquid, so that you would have a better chance of not burning something up in a soldered joint or something. And so you'd want to find what that composition of would be between lead and tin that gives you the lowest melting temperature, you see, and that would be that at that eutectic point there. Okay, so what I'm going to do now is I'm going to draw a partial over here. Actually, I'm just going to erase this because let's see here. And of course I didn't get the timer going here, so we'll start here. I'm just going to erase all this, okay, and start over. And we're going to look at some new microstructures that will show up now that were not showing up on the microconstituents that were not showing up on the original isomorphous diagram. So again, if we have something that looks like this, and I'm just going to kind of draw part of it. I don't need to necessarily draw the whole thing, but let's say again we're doing something like this, something like this, something here, and this is going like this, and this is going up like that. All right, so that's kind of like one side of this, and this would all be A, and then somewhere down the line it would just continue on that way over here somewhere to B, components A and B. Now what we want to do is we want to draw a straight line again, and we're going to just arbitrarily take this line, draw a straight vertical line here. All right, and with this we're also going to know some compositions, and actually what we're going to do is we're going to actually call this the solder, and so this A is actually going to become lead, which is just Pb, and down here B is going to be the tin here at the far end over here. And so we're going to look at this, and this composition, we're going to pick this main composition, we're going to go at 40% tin. All right, now we're going to pick, let's see, 1, 2, 3, 4 points, kind of like we did on the other one before. We're going to pick one here, one here, one here, and then one down here. Okay, and let's see, let's call this, all right, I'll just call this A, B, C, and D. All right. Now I need to check the time here. Okay, it's 9. So, all right. I got about another onto E. Okay. So now what we're going to do is we're going to draw the microstructures here. And against this first one, here it is. This is going to be A, B, C, and D. So this is A, B, C, and D. Okay? All right, so this first one obviously is just going to be all liquid, okay? And we know what its composition is. We'll get to all that in a minute. I just want to draw these new microconstituents for you within this. And this next one at B, there again, there's going to be a little bits, the beginning forms of the grains from, and this is of course going to be alpha over here, alpha grain. So we're going to have the beginning formation of some of these alpha grains, and then the rest of this is going to be all liquid. All right. Now, this is going to get a new name because, again, this is all liquid. This is alpha plus liquid, and this is alpha plus beta here. All right. So notice that we have alpha in this, which is above the eutectic composition line here, all right, the eutectic temperature, and then we have alpha down here. So they're going to be in actually two separate forms, all right, still alpha grains here, but they're going to be two separate forms because one formed above this lower transformation line, one formed this one formed above and this one formed below the lower transformation line there. So they're going to get a new name. So these alpha grains, we're going to give them, a new title, and we're going to call them Pro-Eutectic Alpha grains. Okay, or Pro-Eutectic Alpha. All right. Okay, and then we're going to have the liquid in here. Okay, so down here now at C, we're getting closer and closer to where this becomes all solid, because again, this is liquid to this point, but down here below this eutectic temperature is going to be all solid, a two-phase solid of alpha and beta. Okay, so right here then at C, these alpha grains are getting much larger, okay, much larger, but they're still, again, because they formed above that lower transformation line there, we're calling them Pro-Eutectic Alpha grains. Alpha grains, okay. And there's a little bit of liquid remaining here. Okay, so this is what takes place. There is no liquid below this line here, this eutectic composition line. So we know that. So these grains, the grains that formed above, will remain intact. All right, they will remain intact. All right, and so we're going to put these alpha, and we're still going to call them this. But let's put a little dot beside there, a little dot. So this little dot is going to still mean the I'm just going to abbreviate Pro-Eutectic Alpha. All right. Now, what forms, because whatever liquid is remaining, once it goes below this, turns into a solid. And so what it forms is it forms a lamellar structure, of alternating, you can call it layers, you can call it plates, whatever you want to call it, layers / plates of eutectic alpha plus eutectic beta. All right. So what it's going to look like, this is what it's going to look like. I don't have much room to do it in there, but if I was just to blow it up, well, I'm running out of space here. Let's do it over here. If I did just a microstructure of just that, it would look like this. If this pro-eutectoid is white, all right, so it's going to look something like this, like layers. And so these layers would be the white layers would be alpha, and then these dark layers here would be the beta. Okay, so you see they're stacking, they're stacked layers one on top of the other of these two microconstituents, or these two alpha and beta structures. Okay, so whatever was remaining liquid there now turns into this. So this whole structure now is going to look like this. Just these nice kind of wavy lamellar structure that looks more like, if you looked at it up close, looks more like sort of like a fingerprint. Kind of looks like a fingerprint. Okay, like a fingerprint. Okay, so I need to look at the time here. Okay, I got about 3 minutes to go before I need to shut this thing down. So, so this is what this is look like. This is, again, at this point, which is very special. Now we have two types of alpha here. We've got the pro, and then we've got this. This is called the eutectic. The one inside this lamellar structure. This is called just eutectic alpha, and the other one formed above, the same alpha, but it's formed above, so it's and it stays resident because it doesn't go away. It's called pro-Eutectic alpha. So the little globulars, when you see these, look like little globular kind of things. These will always be the pro-Eutectic, either alpha or beta, whichever side of this eutectic composition you're at. Will always be kind of like little globulars, and then below that, whatever liquid remains here, then we'd have formation of this lamellar looking structure. Now look at this interesting point. Right at this eutectic, all right, right at this eutectic composition, all right, we have no two-phase region here. We don't have alpha and liquid here. All we have is liquid. So this liquid at this point, this liquid goes to alpha plus beta. So in other words, what you end up having is something that looks just like this. It would be 100%. It would be a 100% lamellar structure. All right. A 100% lamellar structure. Only at eutectic composition. Okay? Otherwise, it's going to have these little, like I said, kind of globulars of these different pro-eutectic, either alpha or beta grains involved in that. All right? So that's kind of, in essence, how this diagram works. What I want to do is come back here in a little bit, if not today, tomorrow, and work out some problems, trying to find out how much pro-eutectic grains do we have here, how much eutectic grains are there, and how much of the beta is actually present. In other words, the relative amounts of those. So we need to go through that procedure, methodology, and we'll do so either later today or tomorrow.